Dr. Godez.
Tyler, welcome to the post-class recap on gas laws. And what I thought we'd do today is just go through 3 examples of problems, because that's basically what this was about, was problem solving. So the 2 equations we learned about today was the ideal gas law, PV equals nRT, and then the combined form where we have P1V1 N1T1 equals P2V2 over N2T2. And the only, well, kind of one of the tricky parts is figuring out which one to use in which situation. Right? And so I read this problem sample, 10 grams of carbon dioxide gas has a pressure of 1.05 atmospheres and a temperature of 25 degrees Celsius. What volume will it fill? Right? So are there anything that's changing up there? Are there any parameters that are changing up in this problem?
No, it has the same pressure, temperature, and same weight throughout the entire problem.
Okay, and so this one we have 2 pressures, 2 volumes, 2 moles, 2 temperatures, and so something has to be changing in order to use this one. So it tells us not to use that equation. Right? And whenever I start a problem, I always try to think of, well, what possible equations could I use? I write them all down, and then I decide which one is the one that I actually have to use. So I know I'm going to have to use this one. The second thing I always do is identify what's the unknown. What am I trying to figure out? Well, what am I trying to figure out?
Well, you're trying to figure out what volume.
Okay. And so I'm going to circle the variable that I'm trying to solve for. And I like to solve the algebra before I put any numbers in, because it's easier to move around symbols, right? So if I want to isolate the volume, all I do is divide both sides by P, and I end up with V equals nRT over P.
Ooh, algebra.
Algebra, yeah. Lickety-split. So now I go back and look, so what do I have, and what do I not have for this? Do I have a pressure?
Yes, you do. Pressure.
And it's in the right units, so that's good. I can put that in. Do I have a temperature?
Yes, you do.
And is it in the right units?
No.
No, because we got to convert to Kelvin. And so Celsius to Kelvin, that's one of the things I have to do. R, well, that's a constant, that's the same all the time. And then M, that stands for number of moles. Do I have number of moles?
You don't have number of moles, but you do have the weight of the gas.
Okay, so that's an amount, moles is an amount, so I know I'm going to have to use that to convert. So I'm going to have to go grams to moles. Well, what allows us to convert between grams and moles? That's something you've done probably 20 times already.
Right. Molar mass.
Molar mass. Divide by the molar mass. Okay. Do I have the molar mass?
Yes.
It doesn't say it there, but I have the formula, so I need the formula, carbon dioxide. Well, it tells me that that's CO2. And I look on my periodic table, calculate, 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 and I know that it's 44 grams per mole. Okay, so now I know all the things I have, the things I need to do, and so let's start doing these little processes to prepare before we put it into the equation. Celsius to Kelvin. Well, the equation is just adding 273, so 298 kelvins. Grams to mole.
0.2273 moles.
0.72273 moles CO2. Okay. So I have moles, temperature, got pressure, so now I can plug them in. Plug that all in, and voila. I think it's 5.292 liters. Hard to do that math in my head. Haha. And then I check significant figures, 3, 3, 3. Turns out that ends up being 4, but that's fine. So 3 significant figures I'm going to round off.
Ah, answer.
Yeah.
Alright, so we have a new problem.
Right, so the average volume of a human lung is about 3 liters, that's for one lung. Free divers, people that just dive down, see how far they can get in water without scuba gear, can achieve depths of over 300 feet where the pressure is over 10 atmospheres. A lot of pressure. So what's the average volume of a lung at that pressure? And so again, I've written up the 2 equations that we're working with. Ideal gas law in the modified form. And so what do you think? Is this one where we have one set of conditions or one where something's changing? What kind of assumptions maybe do we have to make in order to do this problem?
Well, we have to assume that the volume of the lung is changing and also that the pressure changes.
Yeah, because we're starting out at the surface. What's the pressure at the surface?
Well, it would be like 1 atm.
1 atmosphere, right. Right, that's the definition of 1 atm, is the pressure at the atmosphere. Yep. And so we're going from 1 atmosphere to 10 atmospheres, and we want to know what the volume becomes. It starts out at 3, and then it changes to something else. Right? So that tells us that we're not going to use this equation. We're going to use this equation.
Right, so sometimes you have to fill in the blanks yourself.
Yep. Exactly. What assumptions do you have to make? So the second thing that I would do, now that I know which equation to use, is I'll look at this and say, okay, I'm trying to work with liters. That means that volume is going to be important.
Right.
I've given a pressure, so pressure is going to be important. And what this doesn't say anything about is moles or temperature, right? And so when you're doing one of these, what I call dynamic problems, where things are changing, other things are constant. If it's not mentioned, you assume it's constant. That means N1 equals N2. That's going to fall out of the equation. I get rid of them. T1 equals T2. That falls out of the equation. I can get rid of them. Right? So this actually becomes a pretty simple equation. P1V1 equals P2V2. Okay, so what's my starting pressure? My starting pressure is P1, right? We decided that.
And that's something you have to assume and fill in the blank yourself. That would be 1 atm.
Okay, so I'm going to say that's 1 atm. And what's my starting volume?
Well, they give you the starting volume, so it's 3 liters.
3 liters, and that's going to be equal to my ending pressure,
Which they actually give you, 10 atm.
10 atm. And V2, that's what I'm trying to find. That's what the question is about. And so presto changeo, I can solve this equation, just divide both sides by 10, and I get 0.3 liters. Right? So if you dive to that pressure, your lungs get collapsed from 3 liters to about 0.3 liters, i.e. a tenth the size. You can actually break ribs doing this.
It sounds like fun.
Yeah, sounds like a lot of fun.